Welcome, David. Thank you. David gave a talk earlier. Elizabeth Bondi from Harvard. Thank you. Noam Brown from Facebook AI Research. Pranit Netrapali from Microsoft Research India. Eva Tardos from Cornell University. And Jacob Forster, I don't know if I'm saying it right, man, from U of T, Toronto. And Aryan Mokhtari of UT Austin. Okay, so we need a couple mics. So we have two mics here for you to. So we have two mics for panelists. There's also that standing mic over there for questions. Yeah, the audience will have the opportunity a few times during the discussion to intervene with questions and comments. There's also a floating mic here with Simon. If you're lazy or something like that, you can flag Simon down. He'll bring you a mic. And I want to welcome you all and thank you for participating in our workshop. And as I mentioned in the very beginning of the day, this is the second time we're doing this workshop. We had last year the first version that was mostly focused on methods, numerical methods, and the math, and the bounds, and a little bit of GANs, but we didn't go very far in terms of applications. So the second iteration right now, we're not getting rid of the math and the analysis that we all like so much, but we are hoping to explore some connections. Yes, let's turn the mics on. Okay, we're hoping to explore some connections between the theory and the applications. So the structure of this discussion is going to be what are the theoretical questions that we're excited about, and we might revisit some of the topics that we have seen during the day. On the other pillar, what are the applications that seem exciting? Okay, so we will revisit some of the ones that we already saw, and hopefully I'll get an answer from you about what applications you're excited, and eventually we're going to try to bridge them. How can application motivate us to go deeper in some directions of theory, if that makes sense, and the other way around, okay? So we're aiming for a discussion of about half an hour, but if it gets heated, we'll extend it. And the audience will have the opportunity to interrupt us. Not quite. We'll have the opportunity to make some comments and questions throughout this, periodically throughout this process. So I will only do this once. We'll go around robin, okay, and we'll start from David. Like a very, very generic question, like in a couple of sentences, what is, in your opinion, the most exciting thing about the intersection of these topics and concepts that we're discussing in the workshop? Like, we can get into the details later, but like the first thing that comes to mind.
Okay, so I read a lot of science fiction as a kid. And there's this quote from William Gibson, who was one of the cyberpunk guys. It was something along the lines of, the future's already here, it's just not evenly distributed. And so, okay, basically he's saying there's always signs of the future right here in the present. And in this case, I think GANs and the sort of stuff we're talking about in this workshop is the future of machine learning, in the sense that to the extent that this field is successful, there's going to be more and more agents out there interacting with each other and interacting with us. So games are going to become more and more present. GANs, adversarial robustness, and the other examples we've been looking at are like little laboratory test cases. They're like the Drosophila of interacting agents. But in 5, 10, 15 years, we're going to be looking at hundreds and thousands of these things interacting, and we need to understand how to do that. So I have no idea how that's going to play out or what kind of techniques we're going to need, but that's what I'm most excited about and expecting to see.
All right, thank you. How about you, Elizabeth?
Yeah, I guess I would just like to echo that and add that I think there's a great deal of opportunity in looking at this interaction between applications and theory, which is sort of the highlight of this workshop today. So just as an example from my own work, we've been looking at these multi-agent interactions happening in the real world today and trying to think about some ways we can apply the theory that we have access to now and make some basically small advances on that to make improvements and actually use these things in the real world. And I think there's a great deal of opportunity to interact with theoreticians to continue making those improvements and making it applicable.
Thank you. Noam?
Yeah, so I agree with what they both said. Also, I think we're in a really exciting time where we're starting to see AI techniques deployed in the real world. And one of the interesting things that happens is that by deploying these AI systems, we're also affecting how the real world interacts and behaves. And so the real world is not stationary, and that also changes the performance of these AI systems once they're deployed. And so I think there's a lot of exciting opportunities in understanding that the world is non-stationary and it is a multi-agent interaction, and the AI systems that we deploy have to be robust to those kinds of changes.
Thank you. Praneeth?
So one thing that's exciting to me in games versus standard optimization is that in games, it seems like whatever algorithmic toolbox we currently have does not seem sufficient. So it seems like we do necessarily have to come up with new innovations in algorithms. At the same time, it seems like the problem in its whole generality is too difficult to say anything meaningful about. So we do really need to understand what the structure that specific applications come with whenever we are writing it in a game format, and use that understanding to actually be able to design good algorithms. So this interaction is what I feel might be very interesting for us as a community to pursue.
Thank you. Eva?
I mean, I like all the things you guys all mentioned, but I thought the obvious question here is in the title of the workshop. Somehow, no-regret learning has been super successful, maybe not as successful as can be, but pretty damn successful in understanding what happens in games. And deep learning is much less successful at that. So we need to, deep learning has lots and lots of practical advantages, and we need to better understand what happens if multiple deep learners are playing against each other, which I think we do not understand.
So I actually want to follow up on that a little bit. People use the term non-stationarity a lot. But I think there's an important and meaningful difference between sort of the non-stationarity of an environment that is randomly changing due to other things that are not under my control, and the kind of non-stationarity that I'm concerned with, and I think a lot of us are concerned with here, in the setting of multiple learning agents. Because in that setting, other agents are updating their policies, are learning in correspondence to my own actions. And that fundamentally changed the learning problem. And I think there's sort of a lot of progress recently in how we can learn better in that setting, but we're really far away from actually having something that can be scaled to real-world problems. Right? So imagine the Amazons and the Googles and the Facebooks of this world doing their supervised learning on data that depends on the data that they generate themselves. I think it's extremely unlikely that they'll be starting to differentiate through each other's update steps to estimate the game mechanics of the setting they're in. So I think there's obviously exciting progress, but we're really far away from having methods that can deal with partial observability, that can deal with other agents that are not co-trained with, that are novel at test time. And I think there's a lot of exciting work to be done, so I'm really excited to be here on the panel.
Thank you. Aryan?
Actually, I totally agree with Eva that we really need to do a better job in understanding the theory behind this deep learning that we are using every day for different applications. And non-convex, non-concave problems related to our workshop is one of the most important problems that we need to study. I'm very excited. I was very excited about the topics that we had about local min-max, the notion of local min-max. I mean, it's nice to look at these definitions, but what we actually need is to come up with a theory for, that provides a global guarantee for all these algorithms. Once you have that, you have a good understanding of all these algorithms, and then you can feel safe and happy to use this algorithm for different applications. But if you don't have a theory to rely on, I don't know if it's easy to basically apply this to, I don't know, self-driving cars or other applications or whatever you want to call it. Yeah.
Okay, I like the combination of the two last responses. The last one says, if we don't have the theory, then we cannot do, we cannot work on these applications. And the penultimate response was started a little bit more pessimistically, like, can this even work in these large systems, right?
I mean, just to reiterate, I didn't say we shouldn't or we don't have to. I just said it feels much better when you have a theory, when you want to apply something on, self-driving cars that are supposed to drive,
right.
Going, in the streets, and you are going to walk around them, right? So if it's an application that is safe and there's no issue to have no theory and employ that algorithm, and it works, it's good. But for
right.
real applications, I'm not sure.
So I'm happy to see already some excitement, so I'm going to let it flow.
So I guess there's a difference here. The way that I understood your response is that we have to understand the dynamics and mechanics of optimizing deep neural networks for a given loss, for a single loss, or you're also considering the case we have multiple agents optimizing different loss functions. That's also, so I think that's sort of the case where I think we have the biggest open question. So even if we did have understanding on guarantees and global optima for optimizing a neural network, which to me already seems sort of optimistic if I think about what we're doing in that setting, then I still think we have a lot of open questions because of the multi-objective nature of the problems that we're facing in reality.
So okay, so let me take that opportunity. What's our best hope there? Like going to multiple agents, optimizing their own, their own objective, under uncertainty, under stochasticity. Which direction should I bet on?
Okay, the first thing I'd say is I don't think there's any hope of global guarantees. Already with neural networks, we don't have them, and we're certainly not going to get them with interacting deep learning agents. It's just never going to happen. So we just have to learn to live with that.
I hope you're wrong.
But I think he's right.
The second thing is we also know, pessimistically, there's an enormous number of negative results in game theory, which basically say we've got no hope of dealing with general n-player games. So we need to start looking long and hard for classes of games where we can make progress and can say something at all. I don't know exactly what that would look like, and that's the kind of thing where it'd be nice if theorists, so Daskalakis has some work on pairwise zero-sum games. It would be nice to have more work of this form, sort of pioneering directions where maybe practitioners could follow instead of having practitioners always be out in front.
So that's a very good point, actually. But if you think of non-convex optimization, it was like that. Like, don't think about min-max optimization, just the non-convex minimization. 10 years ago, I think we didn't have anything solid. But we started looking at first-order stationarity, second-order stationarity, and then we realized for some problems, getting to second-order stationarity is enough, like phase retrieval, many problems. So as you mentioned, for general problems may not be the case, but for problems with the structure, there's hope that you can develop theory and you can exploit the structure of the problem to come up with a theoretical guarantee for deep learning or any sophisticated scheme that you're using, basically.
Sure.
So really quick follow-up, I think there's sort of broadly two avenues we've seen on this sort of like hardest class of problems, which is partially observable general sum. It's either doing the adjustments of the learning dynamics and then also trying to do population-based approaches of exploitability and trying to train these systems robustly. And I think understanding what the limitations and applications are from a theoretical point of view of these different approaches and what the scalability limitations are would be a really good step forward.
All right, thank you for this first round of discussion. Before I go to my next related question, any comments on this or questions from the audience?
I have one. I think we all agree that we need more theory, but so what do you think more theory would unlock in terms of understanding application? What would it unlock? Yeah. Don't know if someone wants to answer. Jacob, you look to want to answer.
I feel like I've said enough, but okay. So, I guess from my point of view, new theory can hopefully provide us with guarantees and robustness. So speaking of self-driving cars, I think there's actually a problem setting that we should think about specifically in detail. Like, what is the game theoretic structure of self-driving cars on the road interacting with humans? It's kind of general sum, but it's not really a prisoner's dilemma. So I think when we start thinking about that in more detail, we can actually potentially develop new methods, and we can have better intuitions for how we should decide in these settings. How can we learn and plan in settings that are both partially observable, general sum, contain multiple agents, those agents are learning themselves? That's a really, really hard setting, and I think theory can either give us guarantees for the methods that we are deploying, but can also help us come up with better learning algorithms, better evaluation schemes, better benchmarking schemes. And unfortunately, I think we need all of the above to make progress on these really, really hard settings. Was that an answer? Okay.
I would say there's two classes of problems. Maybe, I don't know, whatever. I can think of two. The first is kind of what Jacob was alluding to, where you have agents, maybe lots of them interacting with each other and with humans, and you want robustness or safety, sort of, you want to guarantee that nothing unexpected or bad happens. The second class is something more like a GAN, where you are designing a system such that something novel comes out or something interesting. And these have quite a different flavor, and we'd want both.
Actually, there's mechanism design aspect, even if there's many people interacting, like if you know what are the setups in which you can guarantee that learning will do the right thing, you can try to design the system so that they limit the interaction to be of the kind that helps. The GAN is an extreme version of this because there aren't really selfish incentives there. Those are designed also. But there is a design aspect on most interactions in life, like the traffic one for sure. We can set up traffic rules to change how people are interacting.
There's one more question.
Yeah, so I think one of the first steps we need is to figure out what does it mean for a deep learning machine to play a game. One thing I think is that you can't really necessarily say it's going to reach an equilibrium, because these are very, very complicated functions that they're generating. So the idea that they can't maximize or they can't improve their utility by any change in their weights in their neural network, I think it's probably doomed to failure. So instead, we're going to have to think that they're going to get near some good solution, like with GANs, that they draw nice pictures that we like. On the other hand, we're going to have to worry a lot more about the negative possibilities, especially when these interact with each other. And we already have an example, of course, of that in financial markets, where algorithmic trading programs start going back and forth with each other, and they can cause dramatic movements in stock prices in a split second. And the markets have now dealt with that by having limits on how much they can move at any one time. But so I think on the upside, we're going to have to worry about training so they more or less do the right thing, but with a lot of worry about the possible negative cycles that come out from them playing each other, and also then a whole nother set of theory probably for what it would mean for a deep learner to play a human. All right, so when Google's algorithm does page ranking and humans try to game that system, we have examples of that as well. We're going to need theories of what that looks like as well.
Thank you. If there's no response, there's a question over there.
Okay, I'll start with a provocative question and then I expand to a comment. My question is, do you believe that your AI systems are less complicated than a pair of rocks interacting with each other in space? Because if you're trying to understand two rocks attracting each other, you would need much more complicated theoretical tools like Hamiltonians with currents, ergodic measure, and so on and so forth. And I don't see any such mathematical technology here. Most of this is optimization. So do you think that...
I thought the two-body problem was solved, no?
But it's not an equilibrium. The solution is not an equilibrium.
Okay.
So, but here, I would say 80% of the talks, maybe like a significant amount, uses equilibria as the solution concept. So does that mean that Our systems are that simple?
So I'm willing to comment on, no, I don't believe systems equilibrium is the solution. I didn't actually think our talks used equilibrium as a solution, so maybe I'm confused or wasn't listening well enough. Some people can correct me, but a lot of people were talking about maybe trying to find an equilibrium, but was the dynamics of how you find it. So that's not the same as actually assuming there's an equilibrium. And you're right, life is complicated, but I do believe in a pair of simple mathematical models. It does tell you something about life, and maybe I'm a card-carrying theoretician, and that's a true fact. But you know, if you want to try to prove something, you need a simple enough system where you can prove something. And if you do that for a living, you grow to believe that there are messages out there that one learns from this, and I still believe in these messages. So you know, taking a very complicated system and drawing very complicated conclusion, there might be great simulation of real life, but the sort of learnable messages often come from the simple systems with the simple insight.
No, but my question was that in the simplest of systems that I can think of interaction, right? So two-body problem is a very, very simple system, right? But we would need tools that are orthogonal, I think, to the tools that we're talking about right now, right? Like energy, Hamiltonians, other type of techniques.
So I guess like the two-body system is indeed very simple, but the laws are fixed. The laws are fixed by nature. But in many cases, the laws may be up to us. It's maybe up to us to decide. I guess like this may be something that Eva was referring to when she talked about mechanism design and so on, where there may be at least some situations where we are the boss and we can fix the rules. And then in order to figure out what are the rules that work best, these notions of equilibrium might be useful. It's not necessary that they'll be useful everywhere, but it doesn't seem unreasonable to expect that at least in some situations maybe they'll be useful, and in some other situations maybe cycling behavior is the only possibility, and we may have to deal with that in those situations.
Okay, one last question before we proceed.
A little bit, I will try to push.
1 second, is the mic on? Can you? Okay, it's good.
Okay, I will try again to push in the similar question that we heard before from George. So, I am very young, so I would I will use my youth as an excuse. I want to synthesize and over-trivialize what we heard in the conference. So what happened here is the following. Actually, using all of the techniques that I heard were something like that. Look, initially we're seeking the Nash equilibrium. We cannot find the Nash equilibrium because it is difficult. Then we are trying to propose optimistic methods or change a little bit the definition of equilibrium in order to find it. And finally, we are saying, look, the fixed points that we will have, it's a superset of the meaningful points that we define. So I feel something like that we're overusing the same and the same and the same techniques in order to answer the following question: what are the fixed points that we will have? And the fixed points that we will have, either they do not touch the theory that we built, and we are sad, but the real question is what is happening in practice, in GAN. I mean, do we have a function that evaluates those malicious fixed points to say if they are malicious? Can we use that extra evaluation function to put it again in the optimization in order to avoid them and seek only the true ones? And actually, yeah, the feeling that I have is that we are seeking the Nash equilibrium and its children. But right now we are in the moment that we don't seek about that finally. This is something difficult, this is something strange, and we are over trying to define it or specialize it in order to be happy. So are we sure that we are seeking that, or can we define something like that? Maybe we are in the moment like 51 where everyone needs to define the saddle point again to find what is the goal of our system. I would like to hear your opinion about all this over parameterization that I did in the workshop. Thank you.
Any first responses? I admit that I identified a number of points that I can relate to. So maybe I'll use it as an opportunity to go to the next question, which is very related. Is it a coincidence that a number of talks were studying a very similar extension, or let's say change of objective? Like there was the discussion that Nash equilibria are strict, and we need something else. So there was initially a discussion of how, in some sense, dynamic solutions should be considered in Eva's talk in the morning. But then there was Praneeth's talk, there was Tanner, there was Junhao. Like all of those talks consider like a different kind of target, this kind of idea of a local minimax, right? So this sounds, you know, like a new definition that has nice properties, and I'm trying to understand if there's any criticism. Is it the right thing to go for? Like what does it afford us other than some kind of easier analysis? So I'm trying to understand how everybody converged to that idea. How is maybe Praneeth is the right person for that question. What kind of properties, useful properties, does it afford us?
So I guess this also goes back to the previous question where we discussed that for two-body systems, cycling is the only stable behavior. So maybe there is no equilibrium, like point-wise equilibrium per se, and probably this is not the right concept. That's also possible. So in some sense, we have done a lot of work on non-convex optimization, and the definition of a local notion of equilibrium essentially arises from that. And at least in some applications, it seems reasonable that we should expect convergence to a single point. And in many cases, if we end up in a cycling behavior, at the very least, understanding those kind of situations seems harder. So at least from a technical and understanding point of view, this seems like an easier first step, at least that we should understand before we can move on to more complicated final state analysis. Yeah.
Like basically limit cycles?
Limit cycles, yeah. Right. This seems easier to understand compared to limit cycles, and it's not fully clear how useful these are, and even as I mentioned in my talk, they are not guaranteed to exist always, right? So there's not even a question of finding them algorithmically because they may not even exist. So in those cases, probably limit cycles are the only possible eventual solutions. But at the same time, they seem much harder to get to as compared to these things. So this may be looked at as at least a first step in the worst case, and in the best case, at least being useful in some problem settings.
Okay, thank you. I want to shake things up a bit. I would like to go to applications now. That's the next thematic. So there are some, some difficult questions on the theory, on the tools that we use. But going back to the question that, what's going to happen if we solve those difficult problems? Like, what are those, exciting applications? We saw a few things today. We saw a few examples. We saw Elizabeth and Faye's talks where they talked about some interesting security applications and some natural preservation applications, essentially anti-poaching systems, right? And I can imagine a few others in industry, but I would like to hear from you, like, what are some very exciting applications in this future?
So I guess while everyone is thinking, I'll repeat my point and I'll expand it a little bit. I think sort of strategic decision making in settings where there's multiple agents interacting socially, for example, self-driving, is extremely interesting, in particular under partially observable settings. I think what's hard is that we often think about smooth games, we think about sort of gradient-based learners that are optimizing objectives. But really, it's pretty obvious that these agents will be using search and planning and all sorts of other non-differentiable parts within their decision making. So this poses a question for like everyone here in a sense, is the setting that we're thinking about really appropriate for the kind of hard problems that we need to address as a community? And is the smooth games formalism really appropriate in the long term?
What do you think?
Well, I think the answer is probably no in the long term, and I'm trying to figure out if this is a good idea in the medium term and short term. But even if you just think about the paper that we presented earlier, the Hanabi including search, the moment you have search in the process, you no longer have this gradient-based learner. It's no longer just a policy that's going to map into an action from a state, right? Then I have zero belief that the future self-driving cars will consist of a single neural network that takes in observations and spits out actions that's trained using gradient optimization on a reinforcement learning objective, right? So it's pretty clear to me we have to think about strategic decision-making, not just from the learning perspective, but also including planning and search, in particular in partially observable domains, which is just like this really wide open gap as far as I can tell in our theory.
And we have to give up the chain rule? Is that the...
Maybe don't only use the chain rule. Use other things as well.
Okay.
So to take back your example of self-driving car, so you don't think it's going to be like agents like that are alone in the wild and like partially observing the world and trying to cope with that, but do you think it could be designed as a network of agents where like you basically, like you don't train the agent, but also like some sort of bigger network like that use like mechanism design, for instance? It's fun, I know, but...
So I think in the very long term, there'll probably be sort of more orchestrated deployment of these cars. I think in the medium term, we have to deal with settings that contain other strategic agents, both those that were trained together and those who were not trained together, humans, non-humans. And my point is, it's not just a deep neural network. It's not just a smooth function that maps from states to actions. There's going to be planning. There's going to be hard-coded heuristics. There's going to be safety bounds. So we just have to think about what is that setting that we're even in, and how can we formalize this properly as a group, if we want to move towards those kind of application areas, which I think are the most exciting for me personally.
So I don't disagree about planning and so on, but I am very skeptical of self-driving cars. So, okay, in general, I'm a bit skeptical and scared of the real world. So, but where do I imagine applications? So maybe I just because I work at DeepMind, but in general, when I look at the world, I see more and more people just sitting in front of computers all day, every day. Like that's most of our jobs. We don't do much that's real. And it's because the world, I mean, and it's, it's a phenomenon that's been happening for a long time, and it's increasing. So it's because so much of the world is basically accessible through the internet or through computers, right? So that's why we're all able to be productive by just sitting in front of a computer typing all day. So if you take that seriously and you think that like the logistics and the real world stuff is somehow being outsourced and it's somewhere in the back, there's enormous room to have agents that are purely virtual that can do real work by optimizing processes without ever touching a road or a robot or anything. We don't, there's a lot of room to move without getting into the physical details, and we should be thinking about that because I think that's where there's the most opportunity.
So I think two applications that I'm particularly excited about. One is the security games. I think that that work is, of all the applications that I've seen, I think is probably the most mature or close to it. And I think we're going to continue to see growth in that domain, and real-world applications continue to emerge in that area. The other area which I'm pretty excited about, or I think could see real applications in the near future, is financial markets. So I think we've seen a lot of success in applying game theoretic concepts into auctions and other similar settings. And I think going beyond that to something like financial markets, setting up the rules for these kinds of markets to better achieve maximal social welfare. I think there's a lot of opportunity in that area as well.
Any other thoughts on applications? Any comments from the audience on applications? Questions? There's one back there. Simon, I think there's someone back there who has a question.
Hi. I'm not sure if this counts as a question about applications, but I was having a very naive discussion with some other very naive mathematicians. And we were thinking about, so the earlier part of the talk, the conversation was about theory of kind of these differential or smooth games. And we were kind of wondering whether there would be applications of GANs or this kind of like this set of discussions to computational learning theory. So using GANs or generative models as a kind of a new basis for certain kinds of learning theory, as a kind of like a data model. So I can obviously think of this as just like sort of like replacing, instead of talking about probability distributions, you're just talking about generative models. And I'm kind of curious what you guys think about these kinds of proposals. And I'm coming from a completely naive sort of like perspective here, so I don't know what the literature on this exactly is. Yeah.
So if I understand correctly, the question was about the potentially creative applications of modern generative models on statistical learning. Is that the general concept, or?
So I'm really just thinking about it as a way of thinking about, like, okay, if I replace probability distributions and I just think about generative models directly, what kinds of new questions would I be asking if I'm like just a traditional computational learning theory? If I'm like somebody who thinks about like pack learning and VC dimension, questions like this, and I think about like how to characterize like learnability of certain function classes, or I'm thinking about wavelets and curvelets and things like that. Does changing my sort of like my language from probability distributions and to kind of like to a generative model, to something that's or from probabilistic programs to this kind of like a generative model denominated in terms of these large numbers of parameters and architectures, does that give me some sort of juice?
Okay.
So, okay, I could try say some things, not maybe directly answering the question, but something vaguely along these lines. So one thing that's bugged me a lot recently is this word generalization. So in machine learning, generalization typically means the setting is supervised learning, you have some distribution, you sample a finite number of points, and then you want to make claims about how your classifier will do on new points. So we use this word generalization for it. Now generalization is a word from real life, and this setting has got nothing to do with real life. It's completely fake and made up, and it's been a powerful tool in machine learning and so on, but it's just not a real setting. Generalization in real life is more to do with, I walk into a room and there's a bunch of people and I am able to interact with them effectively and maybe order a hamburger, despite the fact I've never interacted with a specific person before. So what I'm trying to say is generalization in real life is mostly about generalizing over other agents. The fact that you can reason about other people's incentives based on very limited information about them. It's a much more subtle, sophisticated thing, but it's fundamentally a multi-agent phenomenon. And I think, okay, so one example is StarCraft. DeepMind did a lot of work on this, and we ran into real problems with generalizing in the sense of training against some set of agents and having the agent that you train perform well against other agents. And it forced a new training regime that encouraged robustness. I think more and more we're going to hit these sort of real-world generalization type problems because of game theoretic and multi-agent settings.
So I guess following up on this a little bit, I do think that we haven't fully understood what GANs are capable of. And I can imagine at some point that there could be a formalism that sort of, puts that adversarial robustness at the heart of how we think about learning, right? And I think this is something, GANs are one example, StarCraft is another example. I think there's going to be a lot of interesting work at the intersection of learning and GANs, using GANs for modeling the world, predicting the world. But I don't have a specific formalism in mind right now how we could replace probability distributions, the real meaning of probability, with sort of like adversarial likelihoods. But it's an interesting idea, so thank you.
There was Schaefer and Wolfk have written a couple books about reformulating the foundations of probability theory game theoretically. I haven't read them, but I know they exist.
Cool.
All right, so because we're soon going to adjourn for the poster session, I have like a twofold question just to wrap up. What does crazy success look like for the field? Is my first question. And what should we focus on next year for the workshop? Either an answer to either of those questions.
Differentiable planning.
Differentiable planning, okay.
I don't know what you should focus on, but crazy success would look like if he succeeds. Take a special case of a class of interesting interactions, multi-agents, not zero-sum, or not at least two-person zero-sum, multi-agent interesting interactions, and in that setting, we could prove that interacting learning algorithms actually achieve something where we can understand what they achieved. If I find any class like this where we can prove such a thing, that would be crazy success.
That's great.
I want to add to that, even crazier success, if you go from crazy to extremely crazy, is not only that we have something where we understand what it does, but this something is also being used by people out there in the real world. So to me, this would be sort of, ultimate super crazy success, or at least those ideas have been adopted by other methods that are being sort of utilized in real applications. So I think that would be really fantastic.
Amen, Jacob. All right, thank you. Let's thank all the speakers. Thank you for your time and for your presence here. This is the end of the workshop.
No, they're still there.
I mean, we have the poster session, but this is the end of this part of the workshop, okay? Apologies for the confusion. You should head over to the posters. It's our afternoon poster session, but this is also the, my opportunity for some closing remarks. I want to thank all of the speakers, invited and contributed speakers, all of the poster presenters, and our panelists, and I should mention the co-organizers, Gauthier Gidel, Simon Lacoste-Julien, Niall Het, right here. There's Nika Haktalab, who could not make it because of visa issues, Rehane Askari, and I think I did not forget anybody, right? Okay, that's it. Thank you so much. Head over to the posters.